In a fraction of a second, something absolutely impossible happened. 3 times the entire mass of the sun was erased from the universe. Not destroyed, not consumed by another black hole, transformed into pure energy. Exactly as Einstein predicted, but never believed we could ever see. There exists a cosmic fabric that holds everything together. Everything. The entire reality depends on it, and when massive objects collide in the darkness of space, they create waves in this fabric. Waves so small, so impossible to measure, that humanity had to wait 100 years just to attempt to hear them. Now here comes the insane part. In September 2015, for the first time in history, we did it. And what we discovered was so violent, so energetic, that the power of that event was 50 times greater than all the light from every single one of the billions upon billions of visible stars combined. A single cosmic event, more powerful than everything we can see. But what exactly was that event? How did we manage to detect something that would be billions upon billions of times smaller by the time it reached us here? And why did a scientific discovery require the construction of one of the most sophisticated instruments ever created by humanity? Before we answer, we need to go back to the beginning of the story, because it all started with a genius who didn't believe in his own genius.
All right, so here's the thing about gravitational waves. You know that fabric that holds everything together? That whole space-time thing that basically defines the reality of our entire universe? Yeah, gravitational waves are like someone threw a giant rock into a cosmic lake, you know? It ruins everything. And where does this completely insane idea come from? Well, in 1916, Einstein pulls the general theory of relativity out of his hat and predicts that these things exist. And his math? Perfect. Massive objects accelerating, like black holes orbiting each other, they disturb spacetime in such a wild way that these waves propagate in all directions at the speed of light. It's like nature screaming, "Hey everyone, something important happened here." But here comes the plot twist. The very genius who invented all this had his doubts, and serious doubts. Physicist Bruce Allen commented that Einstein thought these waves were so weak that it would be impossible to detect them. And worse, he didn't even believe in black holes. Yeah, I'm talking about the guy who literally predicted both things. So, for decades, nothing. Total silence. But then, in the 1970s and 80s, boom, the first proof arrives. And not in a direct way. It was more like hearing the echo of something you can't see. In 1974, 2 astronomers named Russell Hulse and Joseph Taylor discovered an absolutely fascinating binary system. A pulsar, you know, those neutron stars that spin like cosmic tops, orbiting around another neutron star. It's not exactly common, you know? Then, in 1982, Taylor and his colleague Joel M. Weisberg start tracking the radio emissions from these stars. And here comes the insane part. The pulsar's orbit was shrinking. Slowly, but systematically, it was getting smaller. Like, why? Well, the system was losing energy, literally radiating it out into the cosmos in the form of gravitational waves. It's like a couple dancing and gradually getting closer to each other because all that energy is leaking out in the form of, well, invisible cosmic waves.
And you know what the coolest part was? The rate of that shrinkage matched what General Relativity had predicted with an accuracy of just 0.5%. 0.5%! We're talking about math that Einstein did in 1916, matching perfectly with observations from 1982. That's why Hulse and Taylor won the Nobel Prize in Physics in 1993. But here's the important detail. Those were only indirect proofs. It was like knowing it rained because the ground is wet, but never actually seeing the rain fall. What science really needed was something more direct. They needed to detect the actual waves. They needed to measure that tiny, practically invisible disturbance that these waves cause in spacetime as they pass through Earth. And then came the monstrous challenge. How do you detect an oscillation that would be billions upon billions of times smaller by the time it reached here? How do you hear a whisper in a packed football stadium? The answer? One of the most sophisticated scientific instruments ever built in history. We're talking about decades of planning, human ingenuity at its peak, and technology so advanced it seemed like pure science fiction. Its name? Laser Interferometer Gravitational Wave Observatory, LIGO. And when this ultra-sensitive observatory finally managed to capture the signal? Well, what cosmic event, never before witnessed, was so violent, so energetic, that it managed to create a signature strong enough to travel 1.3 billion light-years and still make noise here on Earth? That is the true mystery that was waiting to be solved.
And here comes the moment. September 2015, specifically September 14th, two twin LIGO detectors, one in Livingston, Louisiana, and another in Hanford, Washington, capture exactly the same signal. It's not coincidence, it's confirmation. The signal? It came from an event that never, and I mean never, had been witnessed before. Two black holes. Not just any black holes, but two cosmic giants. One had roughly 29 times the mass of the Sun, the other had 36 times. And these guys were in an intergalactic destruction show that lasted seconds, literally seconds. You see, General Relativity predicts that two black holes orbiting each other constantly radiate energy through gravitational waves. This causes them to gradually get closer. Nothing special. But then, when they get close enough, things get wild. The approach is no longer gradual. It's a chaotic, accelerated free fall. The two cosmic destroyers collide at nearly half the speed of light. And when they smash together, total merger. The two join into a single, even more massive black hole. But here comes the best part. In this merger process, an absurd amount of mass converts into pure energy. We're talking about Einstein's formula E equals mc squared. It's not just theory on a chalkboard anymore. It's real energy, blasted out into the entire cosmos in the form of a gigantic burst of gravitational waves. The numbers? Almost impossible to comprehend. In just a fraction of a second, roughly 3 times the entire mass of the Sun was converted into gravitational wave radiation. 3 suns, gone, transformed into pure energy. The peak power of that event? It was roughly 50 times greater than that of the entire visible universe combined. The entire universe you can see, with billions of galaxies, with trillions of stars, all together, that cosmic event was 50 times more powerful. And that signal traveled 1.3 billion years. It passed through galaxies, black holes, dark matter clusters. It crossed the entire universe. And when it finally reached Earth, it was still detectable by the most sensitive equipment humanity has ever built. Because here's the thing, LIGO is not just any instrument. Each observatory has an L-shaped interferometer with vacuum chambers 4 kilometers long. And its sensitivity? It's capable of detecting a change in the length of these arms smaller than 1/10,000th the diameter of a proton. To help you understand better, it's like noticing a change in the distance to the nearest star, 4.2 light-years away, of the width of a human hair. The ripple that LIGO detected was 10,000 times smaller than the nucleus of an atom. And the engineering behind it? Extreme in every way. The two observatories, separated by 3,002 kilometers, contain the 3rd largest volume of vacuum in the world. To pump out all the air from those tubes, it took 40 days, one time, in 1998 and 1999. The arms are so long that even the curvature of the Earth became a real engineering problem. In 4 kilometers, our planet curves by almost an entire meter. So the team had to level everything with millimetric precision to ensure that the laser hit the mirrors at the end of the arms and not a meter above. This is pure science. It's humanity saying to the universe, we're going to see the undetectable. We're going to measure the impossible. And it worked. This detection opened a completely new door. In the words of Kip Thorne from Caltech, who helped design LIGO, with this discovery, we humans are embarking on a wonderful new search.
the search to explore the warped side of the universe, objects and phenomena that are made of warped spacetime. Because here comes the truly insane question. What will be the next thing we see through this new window into the cosmos? And how will this new way of observing the universe, through gravitational waves, completely reshape everything we thought we knew?
100 years. Let me repeat that. 100 years. That's how long it took from the moment Einstein predicted these waves until someone finally managed to measure them. It's like making a prediction in 1915 and only in 2015 being able to prove you were right. And what are the odds of being correct after so much time? Practically zero. But he was. David H. Reitz, the executive director of LIGO, summed up what this means pretty well. He said that this discovery fulfills Einstein's legacy on the 100th anniversary of his general theory of relativity. Basically, humanity doing its cosmic homework exactly 100 years later. But here comes the important part. This is not an ending, it's a beginning. It's like that moment in a science fiction film where the characters open a door that leads to a completely new world. Gabriela Gonzalez, spokesperson for the Laser Spectrodrometry Collaboration, the scientific collaboration behind LIGO, was straight to the point. The detection is the beginning of a new era. The field of gravitational wave astronomy is now a reality. You know, for decades, people were just talking about this as a theoretical possibility. Now, it's real. It's real science happening. And why is this so revolutionary? Because gravitational waves use gravity, not light, to measure astrophysical phenomena. It's like humanity was blind the whole time, seeing only with our eyes. And now, suddenly, we've gained an entirely new sense. We're using gravity as a detector, as a cosmic ear. This new window into the universe opens possibilities that before seemed like pure science fiction. Black holes we could never see through traditional telescopes? Detectable. Remnants from the Big Bang? Now we have a real chance to study them. And astrophysical objects we don't even know exist? Just wait a little while, because we're going to find them. But here comes something even more insane. In 2017, just 2 years after the first detection, LIGO and the European Virgo Observatory detect a merger of neutron stars. Okay, fine. But then comes the revolutionary part. This time, the event also produced light. Real light. Dozens of ground-based and space telescopes captured the simultaneous emission of gravitational waves and light. Fulvio Ricci, spokesperson for Virgo, couldn't contain himself. This is a significant milestone for physics, but more importantly, it's only the beginning of many new and exciting astrophysical discoveries that will come with LIGO and Virgo. In fact, scientists called that 2017 event the birth of an entirely new field of astronomy, multi-messenger astronomy, because now you're not observing with just one type of wave, you're seeing the universe in stereo. But for all this to work better, you need more people at the party. The reason? Simple cosmic trigonometry. With 2 detectors, you can triangulate. With 3, much better. That's why there are plans to build a 3rd advanced LIGO detector in India. Separated across the planet, these detectors can pinpoint exactly where each gravitational wave comes from in the sky. It's like having ears in 3 different places to hear a whisper in the universe. But here comes the final plot twist. Not all gravitational waves are detectable from Earth. Low-frequency waves, they have wavelengths larger than the planet itself, larger than Earth. How do you place a detector that size on the surface? You don't. You put it in space. Enter the LISA mission, Laser Interferometer Space Antenna. Imagine 3 spacecraft separated by millions of miles, maintaining a gigantic interferometer functioning in the middle of the vacuum. This isn't science fiction. This is in the planning stages. While LIGO operates at frequencies of 10 to 1,000 Hz, LISA will operate at much lower frequencies, between 0.1 millihertz and 1 Hz. Lower, slower, more powerful. And what's the advantage? Supermassive black holes merging. We're talking about black holes that are millions of times more massive than the sun.
To detect the gravitational waves from these giants, you need a detector the size of the sun. Literally, the universe is so crazy that it needs scales of that magnitude. The first detection in 2015, it wasn't the end. It was just the door opening, and as it opens, we see that there was an entire universe waiting on the other side. A universe of possibilities, discoveries, and secrets that are only beginning to be revealed. But then comes the truly intriguing question. What will be the next great mystery that this new way of observing the cosmos will allow us to unravel? And when we finally manage to hear the gravitational echoes of the most extreme events in the universe, those that light could never show us, how will that reshape everything we thought we knew about reality?
Don't miss out. Subscribe to the channel for more cosmic secrets.